Hello everyone. So today I'm gonna do a very specific question. We're gonna find the points of differentiability of this two variable function. And by that we mean, of course, Frechet derivative. Okay, so the main difficulty with this question is the absolute value there. If there were no absolute value, then you would have a C-infinity function basically. And we know absolute value ruins things when it hits zero in the inside. That's why, depending on whether the interior hits zero or not, we have to divide the analysis. So let's see a simple picture of what this function actually looks like. So e to power x is a one-to-one function. That means and also it's a monotone function, so depending on whether x is bigger than 1, which will be below this diagonal. So this is the diagonal, the set of all x's in R2, and here x is less than y, the analysis will change, so depending which region you are. So there is diagonal where your function f is just 0. And on this region, if x is bigger than y, then e to x is bigger than e to y. So f of xy equals e to x minus e to y times x plus y minus 2. And if x is less than y, you're above the diagonal, then f of xy equals negative of that. So this will be minus e to x minus e to y times x plus y minus 2. And again, on the diagonal, you have 0, which actually makes f continuous. But we're interested in the derivative of f. So if x0, y0 is not on diagonal, then on a neighborhood of that, so on a neighborhood of it, fxy equals one of the formulas above. What this then means is that so partial f partial x, partial f partial y exist and are continuous because it's a exponential multiplied by polynomial and are continuous. So we have this famous fact that if you have continuous partials, then f is differentiable. Differentiable not only at x0, y0, but actually on that neighborhood. So that takes care of the analysis when you're away from the diagonal. So we're interested in what happens along the diagonal. So suppose you are now sitting somewhere on the diagonal. So here is x0 and y0. Now let's consider the partials of f, or let's say to compute directional derivative of f in direction I, this coordinate vector I. So you want to move in this direction I, and you want to compute the directional derivative of f. So we have fixed x0, y0 on the diagonal, which means x0 equals y0. So to compute directional derivative in that direction, we will use the formula that applies here, because once you move to the right, and because on the diagonal both formulas coincide, you can assume without loss of generality that it's following the formula for this region. And therefore, we can just apply, because on subdiagonal region, f of x, y equals ex minus ey x plus y minus 2, we have this directional derivative of f in direction I at x0, y0 equal to whatever the partial of this formula gives us. So this will be, partial of that will be e to x multiplied by x plus y minus 2 plus e to x minus e to y multiplied by derivative of that one, which gives you 1. Remember, I'm taking derivative with respect to x, and y is just a constant. That's why these appear. So in this formula, I want to apply x0 everywhere. x0 and y0. But remember, this goes to 0 because x0 equals y0, and I'm left with this quantity. So the directional derivative in direction I will be e to x0 multiplied by 2x0 minus 2. That will be it. Now, similarly, directional derivative of f x0 y0 in the negative I direction. So here, if I move to the left, then I'm using the negative of the previous formula. So the quantity I want will be, but we have to be careful because I will be using the formula that is negative e to x minus e to y multiplied by x plus y minus 2. But so the directional derivative when you go negative I direction will be negative of the partials of that thing. So it will be negative of partial. So remember, partial x by definition is how much you have changed when you move to the right in the direction of I vector. But now I'm going to the left, so this will be negative partial with respect to x of the formula for my function in that region, which is negative e to x minus e to y x plus y minus 2. And this negative and that negative cancel out. I will get exact same formula from the above. So is this good news for differentiability? Actually not. Because I look at partial in direction I get some quantity, and I look at partial in the negative of that, I have to get negative of that quantity, but I don't. I get the same value. So if f was or is going to be differentiable at x0, y0, then we must have that directional derivative of f at x0, y0 in direction I equal to negative of directional derivative in the direction negative I, x0, y0, which forces that e to x0 2x0 minus 2 be equal to negative of that same quantity. And that forces, there's only one way for this to happen. This is never 0, so I can cancel it out. And that means x0 must be equal to 1. So does this say that at 1, 1 I have derivative? No, it just says 1, 1, 1 is the only point from the diagonal that still has some chance. So as a result, f is never differentiable at x0, x0 if x0 is other than 1. Right? So just by considering partial. Now we have to think about 1, 1, 1. So in 1, 1, according to the above, I have that partial is 0. And because you can imagine it's symmetric in the y variable, you also expect the same to be true. So our guess is that maybe derivative at that 1, 1 has to be 0. So let's test this out. So claim is f is differentiable at 1, 1 with derivative of f equal 0 at that point. So what should we do to prove such a claim? Just write the fraction. So we have to show that f of xy minus f of 1, 1 minus this suggested derivative, which is 0, divided by absolute value or norm, say, of xy minus 1, 1 and limit as xy goes to 1, 1 is 0. So this will prove by the very definition of fractional derivative that 0, 0, this is, by the way, a matrix 0, 0, or a vector in this case, that this limit is indeed 0. And what else do we know? We know that this quantity is just 0, so everything simplifies to the following. So equivalently, I want to show that limit as xy goes to 1, 1 of root of x minus 1 to power 2 plus 1 minus 1 to power 2 e to x minus e to y multiplied by x plus y minus 2 is 0. And to see this, I write it so it has two parts. So one part is this fraction that, so I can break this up into two fractions. One of the parts will be this multiplied by x minus 1. And this will be copy of the above plus again copy of the above, and this will be e to x minus e to y, y minus 1. So what I did was rewrite x plus y minus 2 as x minus 1 plus y minus 1. And now the reason for doing this is that I actually can show individually that these limits are 0. So let's consider the first limit up here. This equals my fraction. And then I do the following. So the initial fraction, so let's give this the name A, and let's give this one the name B. So absolute value of A is less than or equal to, so in the denominator, so remember my denominator is this thing up here. And if I ignore one of the components, I get a larger fraction. So that's why I can put just absolute value of x minus y to power 2 under the root. So I made the other one 0. So that just increases my fraction. And I put absolute value on x minus 1 to do that. And then here will be e to x minus e to y. But then the magical thing is that x minus 1 from numerator and denominator disappear, so I get this one. So that's an inequality, so this is true for every xy in R2. So limit of a as xy approaches 1, 1 is 0, because e to x approaches e to y. And the analysis with b is just the same, except this time you ignore the x minus 1 in the denominator and you're done. So similarly, absolute value of b, limit xy goes to 1, 1 is also 0. And that wraps up the solution, because now a plus b limit goes to 0, a plus b limit goes to 0 is saying that this is true, and that means this quotient goes to 0, which means that f is differentiable with derivative being 0. So that's it for this problem. We showed that this function was differentiable everywhere off diagonal, at 1, 1 on the diagonal, and never on any other point along the diagonal. So if you like the solution, if you have questions about the solution, please put in the comments. Don't forget, please, to subscribe to support my channel. Thanks for being with me today. Have a great day.